applications, and we're going to present a case study on fault detection. This session is hosted by our partners, the Smart Manufacturing Innovation Center from Novi Sad. And today in this session we have three panelists, which I would like to introduce. The first is Milan Arapajic, which is full professor at the Faculty of Technical Sciences at the University of Novi Sad. Next we have Darko Čapko, I hope I pronounce your surname right, also full professor at the Faculty of Technical Sciences at the University of Novi Sad. And next we have Srđan Vukmirović from Eternal Company, also from Novi Sad. Thank you again to everybody who's joining this session. Milan, the floor is yours. Maybe we can start recording the session right now.
Thank you. Thank you, everybody, for joining us today. The topic we are going to discuss is about AI in real-time applications, a case study on fault detection. Essentially, our idea was to make the talk or a discussion a little bit more general. So first to start with actually what is the fault detection, what is predictive maintenance, why they are important in industry today, and how do these problems relate to modern advances in AI, essentially in data science, in machine learning, and also the real-time aspect of the entire problem is really industry specific, because quite often the problems that we need to solve in real time to make them useful. So I will just make a short introduction regarding the problem, and then we will go in rounds to discuss more specific topics. So essentially, when we are talking of fault detection and isolation, the first thing is to understand the end part. So what is fault detection and what is fault isolation? The fault detection is a process of detecting that actual malfunction or a fault exists, that the process, the industrial process or a plant or a system doesn't work properly, doesn't work the way we would like it to work. And this can come in quite a few different shapes and forms. For example, the simplest form is a malfunction. It is the case in which a system that was operational at one point stops being operational in the following one. From a fault detection point of view, this is quite easy because simply the system doesn't work. But the question is, the more interesting question is, if we have a working system which starts performing less and less properly, so its performance deteriorates over time. Now, can we detect this kind of behavior as a type of fault? Can we quantify this fault? Can we use some corrective measures to identify this fault? And also, for very complex systems, the question is, where did the fault occur? So the system is not operating properly, and we would like to know why, which part is problematic, and again, this is related to what we can do about it. So when we talk about predictive maintenance, in essence, this is the question of, can we predict that a certain fault is occurring in a certain low quantity in a way that the system is still operational, but we would like to maintain the parts to keep them operational even before they stop being operational. So one of the key aspects of predictive maintenance is to detect when a fault is going to occur, and sometimes in some near future, and then to act before this instant. Of course, really simple way to do it is just to periodically, for example, change parts of machinery. So you know that the nominal time a certain part is operational is, let's say, 1 year. So each year, in annual intervals, you change those parts. But this is essentially not really efficient, because many times you will just waste good parts, good components. So what you need to do is to have an algorithm that will detect that a certain component is not operational, does not operate properly. And this is a really good place, a really good playground for machine learning. Maybe not for AI in its full capacity yet, but for machine learning certainly, because every single aspect, I mean, the two main methodologies of machine learning, supervised and unsupervised learning, both have application here. If we are talking about supervised learning, then we can talk about classifying. We're talking about fault classifiers essentially. So we are talking about detecting whether certain kind of behavior belongs to a certain healthy or a certain faulty group. And this is also an interesting problem here. There is also another interesting problem here, because sometimes we can identify those groups in advance. So we know in advance if there are certain known faults, and we want to detect to which of the known faults does the given one belong to. Also, maybe an operational system can be in several healthy states, but we would like to detect in which one it is. So this is a typical classification problem. However, there is another group of so-called adaptive fault classifiers, which can operate even in cases where it is impossible to know in advance all the faulty working modes system belongs to. And so this is a really difficult task of constructing an efficient meaning that it must operate in real time, but also adaptive classifier that is able to learn from the given behavior and to detect if it is a known healthy behavior, a known faulty behavior, or something completely new, something unknown that is usually also faulty. So this is a really broad topic and a broad field of applications of artificial intelligence in industry. And for example, we know that we can split or divide or classify all fault detection algorithms into three groups. The first one are quantitative model-based group. The second one is qualitative model-based group. And the third one is the so-called data history group. Essentially, the AI applications are in this last one. And one of the consequences on the entire industrial support software is that this type of methods require availability of a large quantity of data. And this data must be collected from the plant, from the shop floor, for a really long period of time. We are talking about months and years. And also it must be collected correctly in order to be rich enough to tell us something about the problem we are studying. And this is essentially something that I would start to I would like to discuss with my co-host here, is related to the way the software is designed today in today's industry. Because as you know, our goal is to get an industry 4.0 shop floor. It's just a buzzword, but it implies that we can have something that is customizable, something that is reactive, something that can be easily fine-tuned to a specific new requirement of the user, of the buyers, of those who want to use the product. We want to have multiple types of specific products that we can change production from one to one very easily. We want to be able to trace the production to see how effective we are, how wasteful we are, how green we are. And all these things require a really deep understanding of the process we are dealing. And so I would like to go one step before and ask, what is the experience of, for example, Darko, you have about the way the industry software has changed in the last, let's say, 2 decades? What is the evolution of the industrial software that is necessary in order to achieve a goal like this?
Thank you, Milan. Industrial software can be viewed from several aspects, divided in several groups.
Darko, we have sound issue. Could be louder a little bit.
Better?
Not so much, please.
Yeah.
Okay, try.
First one is software that monitors the process and collects data, possibly informing the operators about alarms. Second can be software that are integrated for the operation of machines and perform programming and management of the operation, such as, for example, a CNC machine. Next is software for business process operation, for example, job scheduling or optimization some logistic processes. And finally, SCADA software, which is responsible monitoring and control processes. More complex industrial software is usually integration of this type of software. If we talk about software architecture and design, we can say that it has changed in the last 25 years. 25 years ago, communication between software applications was reduced to local networks. Industrial software was dominantly centralized with tendency to develop fault-tolerant systems with redundant servers and duplicated redundant communication channels. Such servers were huge and difficult to maintain. And improvement was done by introducing component-based architecture, followed by standardization in form of, for example, OPC specification and similar standards. Next generation of complex industrial software followed by increase in network bandwidth, internet, and was a distributed system with more potential data centers and more system types. For example, production system, simulation system, and test system in some company operation. With development of cloud computing, next generation of industrial software based on cloud environments and private cloud is mostly used. It is under authority of the company itself, but for certain activities, it is also possible to use public cloud. The use of cloud enables efficient use of resources and is reliable, fault tolerant. Bearing in mind the process of cloud environment, natural improvement of industrial software goes towards microservice architecture as potentially usable concept that enables a significant parallelization. And that is in short.
Yeah. Thank you. Regarding cloud and microservices, Srđan, could you please give us your thoughts on their usefulness and the way they're utilized?
Thank you. My name is Srđan, as I was announced. I'm coming from industry, so I will take a look around the cloud computing and later on blockchain, maybe about industry application. So cloud computing came a long way in the last 15 years, from novelty to now major option for the software development in all industries. So we will use it, of course, in our use cases. But cloud computing had a fair share of that. We can see that cloud computing is secure because we don't have any major data loss in the previous years. Also, scalability was one of the big promises of the cloud, and it is also a solved problem because today you have a data centers all around the world, and as Darko said, the data availability and accessibility is improved, and in future it will be even better. Security and data protection is also very important, but it is now battle proven, and new algorithms are coming into the blockchain, new applications and companies are coming into with the new solutions. So today inside the cloud we don't have any big issues, but now the problem is the data that's coming from the IoT device or the edge computing. So now we have a problem how we will detect who is really sending the data and is this data clear or not, because we have a lot of devices that are outside the cloud, and they have usually they are low cost, so their capability of encoding data and maintaining the data privacy could be limited. So we have to extend more about protection and safeguarding input data. Regarding AI also, in the last few years, almost all of the GPUs that are produced by big companies are integrated in the cloud computing. So the big models are all trained inside the cloud, either in private like Google or Microsoft, or in public clouds. And there are a lot of new initiatives that will allow us or third parties to train our model and later on to use it. So again, AI that is used in this project or this discussion will not be possible in today's dimensions without cloud computing. So cloud computing has become a major solution for the software and system architecture. And my prediction is that it will grow even more, because as I said, most of all the investment are coming into the clouds with the GPUs to use AI. So we need to have more data and more capabilities. But on the other hand, I think that the biggest problem will provide the clean data and how we will stop the malicious users to take over end device or pollute the data. This is the very big problem, and new algorithms again are being created and new technology developed that will help us make sure that the data are clear and that the data are really who they're supposed to be and not polluted. So as a conclusion of this part, I think that cloud computing is now here and dominate the world of computers, and it will become even much bigger in the next year, in the near future. So that's my opinion.
Yeah. Thank you. Of course, you can those who listen to us now ask a genuine question. What does software architecture has to do with fault detection, and why is it so important? And I think it's a good time to state that it's my opinion why I think that it is one of the most important aspects of a modern industrial system in order to facilitate quality fault detection.
Yes.
The main point I would like to stress is that every fault detection, every fault isolation, every predictive maintenance method is essentially a problem of its own, and that it is quite not possible but common. It's always true that people who are developing fault detection, isolation method, predictive maintenance algorithms are not the people who are working day to day in the field. They're specialists, and they need to be able to integrate their solution, the algorithm they develop, the solutions they develop, into existing systems. And this would not be possible if we would have one very central, very monolithic AI solution in which we need somehow to plug into are fault detection software. Obviously, real-time requirements have a number of their own problems we must solve. But the crucial part in having really flexible fault detection mechanisms is to have ability to plug inside the existing software new components, and that these new components can seamlessly integrate with the rest of the system, can pull the data from the system, and also push some results into the system, and also that these results can be then integrated into different parts of other systems. And then we come to another topic I was hoping to raise here, and that is the concept of system of systems, or the concept of software as a service, or here an AI component or a fault detection component as a service, which I think is crucial in order to have really a flexible solution at the end. Now, since we are talking about agent components and AI, it's really a good idea to also introduce agents. An agent would be a software component that is somehow autonomous or can autonomously work with the rest of the system. And since we are talking about agents and AI, in this particular case, I'm not talking about natural language processing agents that are usually mentioned in I don't know, in news, let's say, these last years. I'm talking about adaptive learning agents, and they utilize the third aspect or third modality of machine learning, and that is reinforcement learning. So using reinforcement learning, we can make software agents, so software components that are able to learn from their past actions, to adapt to the environment they are let inside, and also to improve their future actions. And such systems have been used in different fault detection scenarios for quite some time, although they are not at all standard and they're not widespread. So we have a bit of a conundrum here. They're not completely new. They have been existing for decades, but they're still not widespread. And one of the reasons is why. One of the answers is that it's very difficult to create such a system. First, you need a very good understanding of the process, and also you need very good data. And having such a good data was not really available until recently. Another point why they are not as widespread as we would think is that if you have multiple such systems existing in the same environment, there is an emerging behavior of intelligent systems interacting with one another, each with its own goal, and that this emergent behavior is not completely understood yet. It is in the edge of what we know, what we understand. It is somewhere between artificial intelligence, because it can alleviate us from the need to really understand the system before we introduce an agent inside. I mean, obviously, we need to understand something, but the agent can pick up specific parts of what we would like to do. And there comes another problem now. So if we have an agent that is completely oblivious to its problem, then it needs a really, really long time to learn. This is something that we essentially don't have. We cannot put an agent inside and wait for a couple of months for it to get fully operational, or a couple of years. So we need to pre-train it. How to pre-train it? We need to have data in advance. And if this data is available from one specific plant, that is okay, that is good. But sometimes we really do not have so much historical data from one plant, and we need to combine data. And something that is emerging in the last years, I think from 2016, is the concept of federated learning. A federated learning is a concept in which you have an agent that is trained on multiple sites, and yet the data never leaves one site. So the easiest way to do it is to take an agent, train it on a certain database, then move the agent to another location, train it on another database, and go forth. In this way, what the algorithm is sharing is not the data. Data remains private, but the weights of the networks are shared. The properties of the algorithms are shared. In this way, you can essentially have many sources of data, even potentially competing industrial entities that are, at least in principle, able to share data. Now, in industry, this concept is not yet widespread, but in medicine, for example, it is, where especially in the research projects, you use data from multiple hospitals to train, let's say, radiological models to detect cancers and tumors and lesions in images. But the people who train data actually never see the entire data set. I mean, people who train models, the models see entire data set, but the data is never shared. So essentially, this is just one example of problem of sharing the data in industry. So Darko, I would like again ask you to give us your thoughts on this topic.
Thank you. Yes, data sharing is necessary for efficient functionality of distributed computing system. Some of the most used concepts are publish subscribe mechanism and message queue that enables synchronization. In addition to access synchronization, data protection is also very important. Industrial software should be designed in accordance with accepted cybersecurity standards. For example, NIST standard or zero trust concept and recommended procedures. One way to protect data is application of cryptography and data encryption. Today, there are various algorithms for data protection in large distributed and decentralized software systems. In the last few years, they have played a significant role. For example, zero knowledge proof, multi-party computation, and fully homomorphic encryption. So, for example, zero knowledge proof represents an algorithm between two parties, where one party confirms to the other party possession of certain information without revealing the information or data itself. Multi-party computation is an algorithm that enables parties to jointly compute a function over the inputs while keeping those inputs tracked. And fully homomorphic encryption is an algorithm that is used in combination with machine learning and enables encrypted data to be input to some algorithm, for example, neural network. Neural network works with encrypted data and gives output in encrypted form. And after that, the real results can be obtained by decryption of obtained outputs from the neural network. These algorithms are widely used in modern applications, primarily in blockchain and fintech applications. That is short.
So you mentioned blockchain. Susan, could you please give us your thought? I mean, your company is really involved in this.
Can you hear me?
Yeah.
Thank you. So the data protection and data privacy is very important for any kind of AI development, and of course in the cloud as well. And the blockchain is a new and emerging technology that promises to solve the data protection, but again have a high level of transparency. This sounds contradictory, but with the right algorithms, technology, it's feasible. So we can agree, as Darko said, what part of data will be shared, and make sure that only that part of data is shared through some components of the blockchain. Unfortunately, existing blockchain still have issues with the scalability. The number of transactions of data that could be stored in current blockchain are very limited. But we expect that the new generation of blockchain will solve this problem. In our cases, I think that the blockchain can be used as a source of the device ID. As I said previously, on the edge computing or in the IoT, making sure that the device that is sending us the data is really the one that is it should be. We have to have a robust way to create device ID, and for that we can use blockchain or similar technologies. Also, we can then encrypt all the data that is transferred with advanced encryption technologies and cryptography, and to make sure that nobody can tamper with the data either on the data source or in the transport. So to conclude this, in the near future, I expect that the blockchain will have or some of the components will play a big role in device identification that will help us have a better maintenance and prediction of our devices, and that will have a huge difference in architecture and use cases in the future. Especially adoption of AI brings us a lot of data in. And with the training and with the end use of these systems, it is crucial that data are clear, because if we have a bad input, we will definitely have a worse output. So protecting the data sources and validity of the input data, both in the training period or in exploitation, is very important. And we can hopefully solve that with blockchain, advanced cryptography, over some other of its components.
Thanks. Just one more question regarding blockchain. When I was talking about agent systems, one of the problems there is to verify actually that two agents have an agreement, and that agreement is verified. And we should do it without human intervention, essentially in real time. Can blockchain help us there?
Yeah, of course. The blockchain is a complicated piece of technology, but it is the promise is that it can be done without any third party. So trustless system, meaning that you don't have to have a in-front trust in some third party or some upper party, but you can agree and execute part of data or part of code called smart contracts without previous agreement. So it is trustless system, and based on advanced cryptography, you can be almost 100% sure that this is all correct.
Yeah, thanks. And just to start one short round of questions, maybe again from Darko, and then maybe Sergeant, Darko, and I, maybe to reverse what do you think is the important for the future of engineering education, considering the amount of technologies we are facing? And I mean, maybe not just what should the students learn, but how should they learn? So is there any significant changes that you see that are required?
Definitely, the changes are coming in every part of industry, so even in education. Also, it looks like the data is very, or information, so very accessible. Now it's difficult to find out what part of information to learn on. So the university courses or master degrees should be changed, meaning be more agile. But more than that, lifelong learning or constant improvement of your knowledge is now paramount, because 5 years ago nobody even know what is the blockchain or advanced cloud features. So we have to have a better contact with the university and industry and data and knowledge transfer should be faster. It's now, I think, in Novi Sad very good, but it should be even faster because we have almost daily or monthly improvement in the algorithms that in few days or months get into the code. So it is constantly changing, and we need to have much more better integrated university or hubs of knowledge with the industry, especially with the senior engineers. So for university, we now have a good connections, but we need to be more incorporated with the senior engineers having lectures on the university and vice versa.
Thanks. Darko, your thoughts?
Thanks. As Sergeant said, education of engineers should follow new technologies and be constantly improved. There is a tendency for technologies such as blockchain and cryptography to be studied more intensively, regular, and that is additional intelligence. Algorithms are improving day by day. So education of engineers should also follow such progress. Data science is very important also in various domains, and every processing and use of data, the use of modern algorithms represent a special challenge.
Regarding lifelong learning, Susan mentioned, do you think that maybe this should be something that is integrated in universities? So do you think that this is actually a field that universities should step into? It's not typically what universities are doing, but do you think it's maybe time for the universities to step into this arena also? And what do you think would be the best model for this? So for Sujan, let's say first.
Sorry, can I mute? Okay.
Yeah.
So the best model should be to have integrated council between the industry and the university. That we have here in Novi Sad Institute for AI as well. So there are a lot of interesting partners here. But how to make? On the other hand, university cannot change its program every year, even every few years. But we have to have some kind of council or the feedback from industry what is really important for them, and in order to get these courses. It can be a short, like few days courses, but it should be well announced, well prepared. So it takes time, but I think the result will be great.
Thanks, Darko.
It is necessary to motivate students to learn new technologies through some projects in the regular studies, and to follow research papers that is, for example, necessary to do these projects, and to have some combination learning and practical projects and practical teaching system.
Yeah. So just to finish everything with my grain of salt, I think if you take what an engineer should know, just put it on a table, we get a huge quantity of topics, and there are a lot of fundamental aspects that an engineer should learn in order to be able not only to learn the more advanced topics, but also to easily master new topics that are emerging. So maybe, yes, the good idea for the universities is to provide clients. They're no longer just students, they're just clients later in life, to quickly gain new knowledge about new technologies in a well-prepared courses, which would of course have to be also expensive in a way. I mean, not maybe for individual participant, but the amount of resources required to prepare such a course is non-trivial. So probably, do you think that maybe it's a good idea for the universities to offer this as a service to the public, not to rely on a public funding in this regard, or do you think that also the state, the government should invest in this kind of activities? And this is my last question. I think I will end with this.
Of course, it would be great if government can sponsor this. I'm not sure that the government is agile enough to, although the Serbian government has helped a lot with different kind of agencies to promote the transfer of technology and knowledge from university. I think that must come from industry, because we cannot just rely on government, because government is usually not that agile. But at least give a framework how it should be done, maybe to give industries some kind of tax relief if they use that or something like that. It's because I think that the industry had to lead forward, and government should just make it easier to navigate that.
Thanks. Now I would like to Marko?
Okay, I just want to add that right way to improve this system is to enable some people from industry to be in teaching system of faculty, and that is the fact in this moment, and this we should use mostly.
Yeah. Okay. Thanks. Thank you both for making this a much more pleasant experience for me. I would like to ask now if anybody from the audience has a question or would like to give a comment of their own. Thank you. I'm waiting maybe for Professor Zoran.
Professor Zoran is answering email. Sorry, Milan. That's just a question. You mentioned federated learning. This is serious topic, as you know, and very interesting for our previous project. Could you more elaborate a little bit about that? Because if you're talking about sustainable AI could be very expensive sport right now. As we are talking about artificial intelligence, we are talking about cloud possibilities, about security, about all those protocols, about servers, etc., etc. Federated learning is one of the possibility for sustainable artificial intelligence solutions. So could you just more elaborate that from that perspective, sustainability?
Well, yes, of course. In a way, data is a key piece required for making a reliable AI system. If you have problems with data, you have problems with results. And one of the big problems in my experience is that even organizations that are dedicated to collect data, they often don't know what is the reason for data collection in advance, which is completely okay because they don't know what problems they will have. So the data they collect is not completely representative for the problem that they have. And so collecting a vast quantity of good curated data is really, really a very big problem. On the other hand, you have a constant advancement in algorithms. and you need data, you need quality data to train those algorithms. And so we have a problem that somebody maybe have collected and curated really large quantity of data. This data is very specific to this company. It has value. It also have vulnerability issues if it is shared. And the best idea would be not to share it at all. On the other hand, we have somebody who have developed a procedure which is maybe more advanced, and this procedure needs data to be trained. So I think that the federated learning give us the ability or possibility to have independent providers of data which sell, for example, or offer the access to the data for a certain price. And the data actually never leaves their facilities. On the other hand, we have service providers that can provide an adaptive solutions that can utilize those data, and then we can have a small market here in which you are able, for example, to pay a fee to get access to the data which you will actually never see, and then to provide or to sell your product to a third company that actually doesn't really know how your algorithm works or how your data is collected or where it is, but you just push your solution into a software component and push it inside this multi-component system, which is the modern industrial system. I think this is the idea why federated learning may have a great potential for industrial applications.
Okay, you just opened one additional question, just randomly. This is AI as a service. Okay, you have data, I have service. I can provide you service on a distance, things like that. Do you agree?
Yeah, definitely.
Okay,
so
thanks.
It's not only AI as a service; it's also data as a service.
Data, no, to federate learning, data as a service or AI as a service. Okay. Yeah. That's definitely interesting topic to discuss. Okay, thanks. Thank you guys a lot.
Thank you. Question? Anybody else?
Maybe I have muted all others, so if they have questions, please raise the hand. I will unmute you. Okay. So, if no questions, Alexander, could you give concluding remark, or maybe Alexei?
Okay, I can do it. Okay, there are no more questions. On behalf of UNIDO AM Global, I would like to thank the Smart Manufacturing Innovation Center for hosting this session. Big thank you to you, Zoran, and of course to our panelists, Milan, Serjan, and Darko. The recording of the session will be also put on the UNIDO link YouTube page. So we will share the link for anyone who would like to revisit it, and of course for the participants who registered but were not able to join the session. Thank you very much for taking part of the AM Global Forum Week, and see you in some other occasion. Thank you.
Thank you.
Thank you. Thank you.
Thank you.